Enculolistuditus distus.
Elentar vicitur valesus verasto.
Aptecita vara intercastus laboratorio. Nochmal?
Carneval licaravani.
Petio laine poro vahaim cohavio partion discus tamnus geset.
Suole hetilas neles.
Avanto unti.
Euroidinase sopimusasia pöitekiria.
Stopp.
Mustavalco tepleo likinaka saparasfata narasia.
Petolen porovakin kavopi patinoin tikustanuxet.
Perus palveluli kelaitos kuntaitume.
LQ
No, now. Okay, I can't have them on at the same time, so. That's a video I usually show people because that's how fun we have when we hear foreign people trying to speak Finnish. There are, that's for example, not that difficult, that's a whale, so it's easy. Okay, so welcome. Thanks for sticking by so late. Well, you're here for the party anyway, probably, so now you have a good excuse to learn some light stuff. Everyone's fresh and awake, so this is the perfect time of the day to learn how the operating system internals work, okay? Now I'm off. Oh, cool. We're back on. So if you haven't met me before, my name is Sami Laiho. I'm from Finland. I teach a lot of operating system internals, troubleshooting, security, stuff like that around the world. I travel about 200 days a year, so all over the place. I'm now going to focus on operating system internals, but as I had some feedback from the previous sessions that everyone was actually waiting for my Finnish lessons, so let's take a few. I don't have that much time, it's not that tough, so at least you need to know one word in Finnish before you leave this place. Let's start with a very simple one, okay? So the word dog in Finnish, there's not that many different ways of saying dog in Finnish, so you can start with this, and once you've handled these few forms of the word dog, then you can get the rest. So no wonder people are having some hard times learning Finnish, okay? That's it. Now we'll go to the actual topic, okay? I've been waiting for this session, especially after yesterday, because if you are on Twitter, let's start with the worst one, okay? If you're not on Twitter, get on Twitter. Can't be in this business if you're not in Twitter, okay? So let's take, for example, security and think about you against your colleagues. If you have the best possible contract with Microsoft about security bulletins, you can get the information about the new security threat in 45 minutes. An average of those being notified on Twitter currently is 7 minutes. So you'll be 38 minutes late compared to your colleague, okay? So if for nothing else, you do need it. But anyway, yesterday there was kind of an MVP battle going on. So it was this normal thing, Finland against Sweden, as always. So we were fighting, not fighting, but there seems to be a common belief that Windows 10 has a new feature called device guard, and it uses a small virtual machine inside of Windows running on Hyper-V. That's just BS. So that's one part that I'm waiting. It's the second part. We'll start with memory internals, and then we'll talk about device guard. If I'd have to say two biggest things that there are in the operating system itself that have changed, those would be memory compression and device guard. So we'll talk about both of those. We'll start with memory. I love teaching Windows internals. The sad thing, of course, being that when I get people to my courses, I ask them always, and they always tell me usually the same story, and the story usually goes, I've been working in this industry for about 15 years, so now I got to come to this advanced course. I don't understand it at all. Everyone should take the course because that's the basics of how the OS works. That should be taught in schools, and everyone should have that already, but the thing is that it kind of goes the other way. Because it's so weird that you meet people that have been working with computers for 15 to 20 to 30 years, and they'll be on the in the classroom, and they will tell me like, oh, that's how it works. It's like, that's a thing you should have learned already, okay? Windows internals is all about that. So we're going to talk about how the memory actually works, and we're going to talk how security actually works. If you have questions, there's a very, very nice platform in the middle of the expo area, which will have the Ask the Expert sessions instantly after this, which means that I'm going to run there because I'm one of the experts that needs to be there. So I have to be mic'd up and stuff like that. So when we end, I'm going to run there. So if you have questions that I cannot answer here, just go to the Ask the Expert sessions and ask them, okay? I'll be there. I will answer your questions gladly. We never have too much questions on those sessions. I think it's ask@NICconf.com, which is the email address that you can use to send those questions beforehand if you want to. I'm also here for the party, so just come and grab me if you have questions that you want to ask less publicly. I'm from Finland, I know this stuff, okay? No Finn would ever ask a question. That's so funny. I spoke to Mark Rusinovic, and he told me a nice story about two audiences that he's met that never ask a question. And the end result is the same, but the reason is totally different. So Mark said it's two crowds. It's Finnish and Chinese. Finnish and Chinese. Either one never ask a question after a session. But the reasons are totally different. Finnish people don't ask questions because they are afraid that they're going to ask stupid questions, which makes them look stupid, and their colleagues will laugh at them. Chinese people don't ask anything because they're so afraid that the speaker doesn't know the answer. They have so big respect for teachers, speakers, presenters that they are taught from kids that they do not ask questions because there's a possibility that the guy who's speaking doesn't know it. So end result is the same, but the motivation is totally different. But do ask, okay? So first of all, before we can start talking about memory at all in Windows 10, we have to establish some sort of a baseline on what memory is. Honestly, there's no such thing. There's nothing else than memory that has the most misconceptions that people have. I hear this all the time, and I love teaching this because although this might sound a bit, again, like world healing stuff, but the memory is the computer's soul. The computer has nothing inside of it except what's taking place in the memory. There's different speeds of memory. So there's the memory which is in the CPU registers themselves. That's only might be a few kilobytes. Then there's the RAM, which is the fastest memory. Then there's your hard disk, which is the slowest memory. Misconceptions. 1, if you have an SSD, turn off superfetch. One of the most common tweaks on internet. Do not do that. That's just silly. SSDs are Fast, yes, but they're 50 times slower than RAM. So why would you do it? You're just making sure that your fast RAM is not used more. That's just silly. It's like having a factory with workers on standby. You know, you have a factory with 100 people plus 20 in case someone gets sick. Don't do it, okay? So you just use all the resources you have. That same goes for memory. You use the memory, Superfetch uses your memory, makes you read your disk less, because SSDs are dead slow. They're not just twice as slow as your RAM, they're 50 times slower than your RAM. The other one is, another technical thing is that people will tell you that if you have an SSD, turn off defrag in Windows. Do not do that. That's even sillier. That defrag doesn't defrag an SSD because it knows it's an SSD since Windows 7, and it'll do a trim operation, which is crucial for the working of your SSD. So it's not going to do a defrag. It knows an SSD and it only does the trim. So do not turn off Superfetch defrag. One thing I hear all the time, page file is extra memory. That's also totally incorrect. Page file is not extra memory. It's also said that page file is virtual memory. That's also incorrect. Page file is not virtual memory. If you take away your page file, you still have virtual memory. Virtual memory is the concept. It's the abstraction layer between your physical memory and your operating system. That's virtual memory. You will have that whenever you take off your page files. Virtual memory is not going anywhere. People will tell you that you take away the page file so that your computer doesn't page. That's also silly. You don't take away the page file and say that now my computer is faster because it doesn't do any paging. Well, page file is a packing store for your memory, but so are all mapped files. You still have thousands of mapped files on your machine, which all will incur memory faults, which will result in page faults, which will result in reading your disk. You're not taking away paging by taking away page file. Paging happening all the time. It's a normal way Windows works, and it's supposed to be there. When you open up a Word document, the Word document has to be read into memory, but not everything yet. First, you can read just page 1, 2, and 3, and 5, because that's the fastest Windows knows that you could quickly go through those pages. It doesn't need to preload page 72, because that page 72 you will not. It's not that common that you would skip to page 72 instantly. That's in a that docx file. That's a very good example of a mapped file. It's mapped to your virtual memory, and then when you try to read it, if it's not in memory, it's read there, which is a page fault. That page fault is then solved by the memory manager. There are a lot of misconceptions. So, for example, page file is extra memory. It's nothing to do. Remember a few basics. If something is in your page file, it was once in your memory. Nothing can be written to the page file without first writing it to the memory, and then it gets paged out to your page file. Because if page file was extra memory, that would mean that if we do a memory dump of your machine, we would have to dump all your memory plus all your page files. You don't do that, you just dump the memory, because nothing outside of that memory is important for the state of the computer currently. So you can't draw like, this is my memory, and then this page file continues that memory, gives me more memory here. No, it's a packing store for your memory. Virtual memory is there to make a developer's life a lot easier. When a developer creates an app, if we wouldn't have virtual memory, every application developer would have to start creating a new application by going through your physical memory to see if there's anything free. Now everyone starts with the address of 0. Every single one sees the same virtual memory, and the application can believe that it's address 0. And then your memory manager maps it to a physical address. Otherwise, everyone would have to start from a different address. So virtual memory is there as an abstraction layer between your physical memory and your operating system and its applications. There's a big change if you're coming from Windows 7. Now this is a slide that I'm always thinking if I should have it or not, because I'm always talking about, quite often I'm talking about the newest operating system in conferences like this, and people quite often want me to go through what's new after the previous one. So now it depends what is your previous one. If you're already in 8.1 and you're now going to Windows 10, then this doesn't change. But if you're on 7 and going to 10, as most people are, then this changes dramatically. The same thing changes between 8 and 8.1 and Server 2012 and Server 2012 R2. If someone will tell you that there's not a big difference between Server 2012 and Server 2012 R2, that is ridiculous, because the difference is astronomical. It's almost bigger than ever before. Now, what you see here, on the left-hand side, there's a 32-bit notepad running on any Windows. It sees a memory, a virtual memory of 2 gigs. Why 2 gigs? Because at that time when Windows was introduced as a 32-bit operating system, that 32-bit translates to a decimal number, which is then easy to see that that is the amount of 4 gigs. So 32 bits can address 4 gigs of memory. Now that needed to be split in 2. Half goes to the kernel mode of Windows and half goes to the applications. Now, that might sound a bit smallish nowadays. It's ridiculous that you have 16 gigs of memory, but your application can only use 2 gigs. Some cases 4 if you have what's known as large address space aware flags on your applications, but basically 2 gigs. But remember that this was introduced into NT back in 1993. And back in 1993, an average high-performance desktop computer had an average of 8 megs of memory. So 2 gigs was astronomical. That was designed to never run out. Nothing's more stupid in IT to say that this will never run out. That's like saying IPv6 addresses will never run out. Sure, like 3 years from now when we're expecting a IP12 or whatever they're going to call it. So resources will run out of those. So what happens when we move to anything up to Windows 8 or up to Server 2012? Then on a 64-bit operating system, Microsoft is able to use 44 bits of memory. Windows is far from using 64-bit memory. Windows up to 8 and 2012 uses 44 bits of memory. That 44 bits translates to 16 terabytes, which is cut in half. Your operating system gets 8 terabytes, and every application that is 64-bit gets 8 terabytes of memory. It's never supposed to run out, so it doesn't matter how much memory you have. It's supposed to be astronomical compared to that, okay? Now, when we go to 8.1 or 10 or Server 2012 R2 or 2016, then Windows is able to use 48 bits of memory, which translates to 256 terabytes. That's why on the right-hand side you can see the 64-bit notepad getting 128 terabytes of memory. Every application in Windows believes it has 128 terabytes of memory. So does your kernel. 256 spread in 2, but we're still nowhere near 64 bits. We're up to 48 right now. So that's a very, very big difference. Now, does it matter, honestly? Because if you think about your servers, for example, Server 2012 compared to 2012 R2, does it really matter if I can use 8 terabytes or 128 terabytes? Well, you have to be a very, very hardcore power user of Notepad if you're going to use that amount of memory. But if we think about Excel, for example, you know people get crazy. Excel is like its own parallel universe. The amount of data people try to fit into an Excel sheet is just as astronomical as this. Well, anyway, does it really matter? Maybe now it doesn't matter that much, but there is an aspect that we haven't talked about, and that's security. Because Windows, since Windows Vista has supported something called ASLR. And this randomizes memory addresses for processes. So when your process sits in Windows, you know it's so ridiculous how Windows security works, because in Windows there's one single bit in your memory which says if your password is correct or not. Even in Windows 10, there's one bit. If it's 1, password is correct. If it's 0, password is incorrect. Doesn't matter what you put there. So what we do is we attach another device through FireWire, Thunderbolt, whatever that can access your memory, some dangerous bus. And we go and find that bit, change it to 1, and then you can use whatever password you want. Everything will work. It'll just let you in because it's correct. It says it's correct. The bit is 1, so it's correct. Okay. This is heavily used by devices you can buy. This is totally out of agenda. I wasn't supposed to show this, but maybe I will. So windowscope.com sells these devices that use this same technique. Windowscope sells devices. They have the coolest ever references that any company has because their customers are NSA, CIA, FBI, whatever 3-letter acronym US uses. So they just sell these devices that you use to access computers. Just plug it in and it opens any computer. So for example, this one, Capture Card Gateway, that opens any computer, costs $6,000, but the price is, I always say this, the price is ridiculous for both poor and rich. Because you would never pay $6,000 to get into a computer. Because you can do it for free. Let's get back to that tomorrow on another session. But anyway, also NSA, that's just a nominal price. Needs to be there so that there is a price. It could be, as well could be free. Because they pay 100,000 euros per a mobile phone encryption or decryption device. So that's just a ridiculous number. It's so low that it doesn't matter anything. Just has to have a price. So it's, for both poor and rich, it is ridiculous. Now, what does ASLR mean? ASLR means that since Windows Vista, the location where that bit is has been randomized. It was in a static place up to Vista, which meant that we knew where it was. So we just went in and changed it. But now we have to search for it. And now we get to the freaking big virtual memory. Because that's a virtual address that they're looking for. The more addresses, the longer it takes to find it. So even though you don't need it for your applications, your security needs it so that we have more field where to hide things. Okay? So it is important, although might not sound like it first. So what happens in memory normally? Normally what happens in memory is that sometimes we're running out of memory. So Windows takes stuff out of your memory and puts it on a slower device sometimes because it's either running out of memory or it's just optimizing. That's what people hate. They want to block this because they hate optimizing. It's the funniest thing. People will tell that I will tweak my memory settings because this guy on the internet showed that there's this how to tweak performance of Windows. I read it. And now I take away my page file, I do this and this and this, and then this game is faster. Yeah, that game is faster. That's a good trick for 1% of users, maybe. Less than 1%, absolutely. Like 1% of a percent of a percent or something like that. Some people might. There's only one article on the internet that I've ever read that's good for tweaking Windows. That was published by Ars Technica, written by a guy who works at the kernel team at Microsoft, and I'll tell you the whole article now. Because the article said, install Windows, keep using it. James. It's the only thing you should rely on, okay? It's like if you're one of those percent of a percent of a percent of a percent, go ahead, tweak your stuff. Take away page file, for example, some Office versions don't even start. They will tell you, you don't have a page file, I'm not gonna run. So, like for maybe gaming, playing a single game, not a multi-purpose computer. But otherwise, you do not touch that. Because if you sacrifice your page file, you also lose all ability to get a memory dump by default, which means that you can't solve the toughest problems, which with Windows 10 we do again have some blue screens, okay? Page file is needed for memory dump, so it has a reason to be there. Now, when Windows starts what is known as trimming, Windows starts to trim memory to give it to people who need it more, or in this case, processes that need it more. So Windows does this. So on the left-hand side, you can see a working set. What the heck is a working set? In Windows, you see that term all the time, but if you don't know what a working set is a process's private memory which is resident in the physical RAM. Process might have a lot of memory, but some of it can be paged out. So this one that is actually in the physical fast memory, your RAM, that's known as the working set. Now, if we need to trim that, because someone else needs those fast physical RAM pages, we'll trim them out of the process. And while we do the trimming, that page will move from that process to what is known as a modified list. Why? Because it's still in memory, but it's not backed up by any backing store. It hasn't been put somewhere to be repurposed to use for something else. It's not packed up yet. It's on the modified list. Now it needs to be written to a backing store first. That backing store might be a file itself in a Word document, or for your RAM in general and your OS in general, that's your page file. So then it gets written to your page file. That's when we can put it on the standby list. What's a standby list? Standby list, it's the same memory page with the same content that it was before, so it's cache. It's sitting there because it's very common that the process that just gave it away will need it instantly again. So it's cached. One big concept that people also get wrong is that they will look at their computer. Oops. They will look at their computer and they will tell you, oh my God, that's the wrong tool. Sorry, Resmon, not Perfmon. This is what I was trying to do. Don't fail me now. Come on. Yes. Ooh. The lights. Where's Resmon? Here we go. Resource monitor, memory. And you look at this line here. Oh no, I only have free memory of, 9.6 gigs. That doesn't look that bad. Honestly, you never look at free memory. Free memory is unused resources. If you have free memory a lot, you start to cry from now on, okay? If you're still happy before this session, forget it. That's just silly. Don't want to have free memory. The more you have free memory, the worse you have to feel, okay? You use all your memory that's possible because that's faster than using your disk. So what you're looking for is available memory. That one you want to have. But that available memory there listed on the top of those numbers, that is the sum of your standby lists, which is your cache. So it's stuff that can be given to other purposes if needed, but as long as it's not needed, we'll use it as a cache because that makes your computer faster, okay? So you do not look at free, you look at available. Back in 1993, Mark Russinovich got famous because back in 1993, the most sold program in most sold software in the world was Windows 95 Upgrade, but the second most sold software in the world was a tool called Cacheman. That was a tool that could be used to free up memory in Windows. You ran it and your task manager suddenly showed you have huge amounts of free memory. It was an awesome tool, except it did nothing. So Mark Russinovich showed that it doesn't do anything. He became famous, the company went bankrupt and became a nice story. What did it do? It filled the whole memory with its own stuff, forcing everyone else out of the memory. And when it had forced everyone else out of the memory, making your computer slower than ever, it stopped itself. So your task manager looked like it had huge amounts of free memory. The only thing it was doing, it was just forcing everyone else out of the memory, making you less efficient. But it looked damn good. So I feel quite bad. Shouldn't pay this much for a freaking Surface Book if I don't use the memory for anything. Well, honestly, of course I do. I run Hyper-V. I need that memory for my virtual machines. I'm talking about when you're running your normal workload, you shouldn't have more memory than you need. That's unless you let Windows do something wise with it. Otherwise, you're paying for nothing, which is just silly. So now, when this trimming takes place, this standby is your cache. So things go there because they might be used by someone else. But they can't be given to anyone else yet because they have content in it. You can't give another. Let's say you have your password manager. Your password manager has just saved your most critical password in memory. It's in these two memory pages. Here, you can't give it to Notepad. It has your memory. It has your password in it. So it has to be zeroed out first. So it'll actually go to what's known as a zero-page list, which means that first there's a zero thread which will clean it out. It'll write zeros to every bit on the page. When it's cleaned out, then it can be repurposed for something else. But it needs to be sanitized first, okay? That's why you can't give it straight to another process. It could go to the same process, but if it goes to another one, it has to first be zeroed out so it can be taken to the free list. Now, the problem here is with new devices and page file. Not just that page file is slower than memory, but now we come to a place where we honestly don't want to be. We've got a lot of Surface books and a lot of nice Ultra books here, which means that I'm quite sure many of you have an SSD. And now we come to the other problem here, which is that like this never before applied, but nowadays it does. Even though it would be wise to put something in the page file, now you don't want to do it because your SSD wears out. SSDs wear out by writing to it. So now Windows has to behave differently. It can't put stuff there anymore, not just because it's slower, but also because it'll kill your SSD gradually. Few things that are totally out of scope for this session, but think about this as well. Remember, SSDs get dead slow if they're full. That's why you can't buy a 1 terabyte SSD. When you buy a 1 terabyte SSD, you buy a 1.2 terabyte SSD. All the manufacturers put extra cells there just to keep it running even if you fill it up to 100%, because it wouldn't work. So SSDs get dead slow. SSDs can't replace a page if they want to. They have to or a sector. They have to work with a block. And these blocks are not 512 bytes like we had for hard disks. These are like megabyte sized chunks. And an SSD can't write to anything else but an empty cell. Which means that if you don't have these empty cells, it has to take a cell, read everything from it into its internal controller, change the data, and write it back to that empty cell. If you're filled your SSD up to 90%, it has less free cells. It becomes very slow, because every write operation requires reading everything from the block first to the controller of the SSD and then writing it back. So don't buy a 32 gig SSD and be happy because you still have a few gigs left. Buy it big enough so you don't fill it up to like 75%. That's a lot better guideline, okay? Now, we need to take care of this. So, if memory, I've been trying for years to figure out a way to talk about memory, so now I'm trying another way of approaching this. Let's say we have a table. So there's a page table, okay? You could think of it as a physical table. If you put A4 sized papers there, you can't put them on top of each other. That doesn't work, okay? So you have to put them side by side. So there's quite easily, there is a maximum amount we can fit there. So now what if I want to get another page there? That means that I have to take one out, okay? So that's when our page file comes in. So now we'll move that page into the page file so that we can get another page in. That's how Windows has worked. Highly simplified, that's how Windows has worked for decades, okay? What's the other way of fitting more papers next to each other on that same table without putting them on top of each other? Okay? Squeeze them. Make balls of paper. You can fit a lot of them on the table, okay? That's Windows 10 and memory compression. Now the problem is that to read any of these papers, you need some resources to first unwrap the paper, read the contents, and maybe wrap it again, okay? So that's what people haven't been doing because the problem is that you need CPU power. So if you get more memory, the problem becomes that you lose CPU power. But nowadays, that's not an issue. So what happens here is something totally different. So what happens in Windows 10? Now, when Windows needs to trim something from a working set, this would be very good for a small device with small memory. Think cheap tablets under $100. Very small memory, okay? But it's good for you because of your SSDs as well, for every one of you. That's why it's on by default. You can't switch it off. There's no settings for it. It's on and it's there to stay, okay? So what happens here is that instead of writing it to the page file, they compress it, but still keep it in memory. which means that we have free pages which are already sanitized because they're compressed, so we can put them in the free list and someone else can use it. So we will do a store inside of memory which houses compressed pages so that we have free pages more. Before writing anything to the page file, we try to first squeeze it and put it inside, and I have no idea why they chose it, but they chose the system process to do it. So that's why if you have a brand new Windows 10 build, you will actually, if you go to Task Manager, the new, that's the funniest one, the new improved Task Manager. Have you heard that joke? The improved thing? Like, it's even worse than ever before. No, I mean, I know what you mean. Yes, it looks better. Yes, it has more information, but it's lying more than ever before. Because before, remember, this one said applications. Okay? So it didn't have anything to do with applications. Yes, but at least we had this that said processes, and that was talking about processes. Now this one says details, which has nothing to do with details, and this one says processes, which have nothing to do with processes. So it's less correct than the previous one. Anyway, if we go here and you find this, system and compressed memory. Now there's this word. This one didn't exist in the previous builds of Windows 10, so it's been there for a few builds for people to know what we're talking about. It used to say just system. And then people started complaining because they saw that there must be a memory leak. There must be a horrible memory leak in Windows 10 because the system is now using more memory than ever before. And it's growing all the time, constantly. It's memory leak, alert, alert. No, it's just fine. It should be using more memory because that memory that's used is actually used by this compression. Everything that goes there stays out of your page file, which means your SSD doesn't get written too. You get more life for your SSD and you get a faster Windows. Okay? So you can't even turn it off. It's been there for a while. We actually talked about that already. So here you can see that's the old Windows 7 Task Manager where system is taking some few kilobytes. And then you get another one here, which is from Windows 10, which is 82 megs. So I agree, it looks like a memory leak, but it's far from a memory leak. Should we do it? Yes, we should, because we have such great computers nowadays. Everything doing compression, uncompression used to be an issue. Nowadays it's not, especially for memory. Think one page is 4K. So 4 kilobytes or sometimes even bigger, but at least 4K is one page. So now a 3-year-old laptop can do 300 megs per core of decompression. But that fits a lot of pages. Every page that you can use is away from your page file, better for you. Current laptops with 8 cores, 7 gigs, lowest end Windows Phone. This is done on a Lumia, I think it's 550 or something like that, which this one is measured from. So 250, 300 megs per second. That's why even your mobile phones use it. Everyone can do it. It's not a question of losing CPU. It's a question of just having a faster, better working computer with a longer lifetime for your SSD. It's also organized, so there's no defragmentation, no fragmentation issues. So it's just good for you. I have no idea how I can talk 35 minutes of memory compression. Amazing. Amazes even myself. Now, even more important than memory compression is this one. I love this part because this is the part that you hear in every single other conference that I've ever been to, and you hear all the Microsoft guys, even them, you hear them telling the story of a small virtual machine inside of Windows 10. It houses your hashes and your secrets. It's running on Hyper-V. You can't access that. No, it's not a VM. It's not. It's using virtualization technology, yes, but it has nothing to do with a VM. Let's think about this for a while. What if we have just a basic situation that we have in Windows normally? So my clicker is maybe working? Now, Windows is divided in 2 modes. Kernel mode, Wild Wild West. Everyone uses a shared memory, and anyone can do whatever they want. Many people say processes in kernel mode, wrong. That was even incorrect. I wasn't aiming for that, but that was even incorrect because there are no processes in kernel mode. But some people will tell you that kernel mode processes have full access. They have full control. Well, you could actually easily say that kernel mode threads don't have any access because there is no concept of access. There are no limitations. The kernel mode is a wild, wild west. Anyone can do whatever they want. The problematic part here is that anything that runs in kernel mode, let's see, how many of you believe that you can actually extend Windows's kernel? Do you know how to extend Windows's kernel? No one, okay? I'll ask the same question with different words. Is there anyone here who can install a device driver? Okay, quite many, yes, because it's the same thing. That's extending your kernel. That's the problem here. Windows kernel can be extended by device drivers by any of you who have admin rights, okay? So you extend the kernel, and any driver that's in the kernel has ability to read every process. Now, I'm not here to talk about pass the hash in a way that most security sessions will. They will show you if you use Mimikatz, if you use Windows Credential Editor, you can do this to pass the hash and attack a computer from here and here and here. I'm not here to talk about that. I'm here to talk about the concepts why that works. So let's take this a lot more simplified, okay? Let's take a command prompt. And let's do this. Sysinternal's tool called process dump, okay? Proc dump LSAS. LSAS is the process that's responsible for your authentication and storing your hashes. That's the one that Mimikatz attacks. That's the one that Windows Credential Editor attacks, whatever. Every one of these things that uses this pass the hash techniques is attacking this process, and it needs to access its memory. And you can do it with this. I have now the contents of all this computer's LSAS, which means I have all the hashes needed to attack the other computers if pass the hash works in your environment, okay? Now this concept needs to be blocked because the problem is that whenever I have any device drivers in my machine, they can read that memory. Now I have the dump, I can give it to you. You can take it to your computer, use Mimikatz and extract those hashes if you want. Mimikatz has an option to use a dump file instead of live memory. So now, this is the big problem. That's why it's impossible for me to protect you from pass the hash attacks usually, because I can't in any way block kernel from reading that part of the memory where it is stored. So, what Windows 10 does is it introduces something called Virtual Secure Mode, VSM, also known as, some people talk about device guard. Well, device guard can technically be run without this, so it's an addition to it. But VSM, Virtual Secure Mode, is what people think is a VM. As you see, it's running on Hyper-V, so it requires a virtualization technique to work, but it's not a VM, because let's think about this. What if I have 16 gigs of memory? And we would do this the simple way, which would be, by the way, to create a VM. So what if we would create a VM and put that LSAS in there? We would be able to block anyone from reading it. But we would have to sacrifice memory. If you create a VM, you have to give that VM part of your memory. So if I would divide my Windows, let's say, in half, let's do a normal kernel and a secure kernel, but let's put them in VMs. That would mean I would have to say that, for example, let's give 8 gigs to this normal mode and 8 gigs to this virtual machine here. But that's not happening. You're not. That's why I yesterday on Twitter asked someone that a exercise question: how much memory does this device guard VM that you're talking about use? If there's a VM, it has to use memory. You have to have, like, let's give 1 gig to him, and we'll use the rest. That's not happening. I have all my 16 gigs of memory, as you saw from the resource monitor. I'm still running this. So there is no VM. Instead, what there is 2 kernels in Windows. So this changes the Windows structure dramatically, fundamentally, okay? So Windows is now divided into 2 modes. There's this normal mode where your kernel mode is, where you can inject drivers if you want. And then there's a user mode with the LSAS process, for example. But next to it is a secure kernel. You can see it on your task manager. If you go to these details, you find your normal system is running here. This one. And also, you should see another one, which is here. That's a good implication that you're running this technique, this technology, because this is part of your secure kernel, okay? Now we're running that, but then on top of that sits the place where we put things that we want to hide, which is known as isolated user mode. So the good thing here is this. From the normal kernel, with any kind of device driver like Mimikatz or whatever, they cannot access that LSAS process. It's not LSAS, it's called LSA ISO. LSA ISO.exe sits on that isolated one. We can't access it. Now this is a part where you can't cheat by having admin access. That is below the operating system. That's on the hypervisor level. So it's actually not a full kernel. It's a, you could say it's a proxy kernel. I'm going to go through a few of these because I want them to be on the video, but I'm actually explaining them here. So what actually happens is that we don't have two full-sized kernels, because that would be also silly for resource-wise. Meaning, let's say on the secure side, I want to save something in the page file. Now you have to remember there are no VMs. If there was a VM, that VM would have its own page file. You would need resources for that as well. But we're using the same page file, but I want to put stuff there, which might include my passwords, but the normal kernel can't read it. In comes encryption. Kind of easy to solve. Let's encrypt the page first, then ask our normal kernel to write it to the page file, so that we don't have to do everything. Just ask the normal kernel to do it. Now, if the normal kernel would, on the other hand, encrypt it, that would mean that it would have the keys to decrypt it. So crypto code is an example which is actually built into both kernels. Secure kernel has its own crypto code, because it cannot rely on the normal kernel to write encrypted stuff. Now it can put stuff into the page file, encrypting it itself, storing the keys in the secure mode, and then asking the normal kernel, could you please save this to the disk, please? It's done through this, oh my god, I can't write. Shared buffer called Marshall. Don't go Google that, won't find much information. Marshall, okay? So, not Marshall, but Marshall. So what this is, like, it's like if you go to US and you want to cash a check, they still use checks. I hope you don't. We don't. But I get paid with a check in US usually if I'm speaking. So they give me a check and I need to cash it. If I go to Finland, it takes 2 weeks to cash it, and I lose about 20% of the value. So I want to cash it in US before I fly home. So I always go to these check cashing kiosks. And that's a place where you have this plexiglass. Basically, you have access to all the resources behind that plexiglass, as long as you can be nice enough to ask that lady behind the plexiglass to do it for you. That's what's happening here. That small box there is like the box you have below the plexiglass. You can put your check there and slide it on the other side. They put money and slide it to you. So this one sanitizes every single query that goes from the secure side to the normal side. Needs to go through this Marshall. Now, this all sounds fancy, but it raises a question. How come the kernel is not able to access the memory of the secure kernel? Because we just stated before we started this that kernel has access to all memory. Your kernel can access all memory. So how the hell can it not access the memory that this secure kernel accesses? That's the problem here. So, bear with me. I know I'm standing between you and the party, but bear with me for a while still, okay? So, here we have a normal virtual address space thingy. So in Windows, this is known as the first level address translation. What it does is that this process here believes to be writing to a virtual address 6789, but it has a page table that actually tells that memory manager knows that when it calls for this one, it's actually a physical address called 0x7777. Now another process can do the same, ask for the same address, but it's translated to another one. That's the basic function of a memory manager and virtual memory concept in Windows. It also has an access mask saying what can you do with that piece of memory. Can that page only be read from, written to, or executed? Also has an access mask. Now, this is first level address translation, okay? Well, kernel has access to those page tables. So, can it just change the page tables? Now, that's when Microsoft thought that now we need to talk to the Hyper-V guys. That's why people think that's a VM. Even inside of Microsoft, they believe it's a VM because they're talking about virtualization technologies, yes. So now what happens is, that's a totally another example. So what happens below your virtual machine? Most of you are running virtual machines anyway nowadays. So what happens below that virtual machine? Well, your virtual machine here believes that it has a physical page called guest physical address. So it believes it's 67890. But it's not even that, because it's actually a system physical address of 0x77777, okay? The VM here believes to have a physical memory address of 67890 as well, but it's taken care by your hypervisor to be pointed to another physical address on the real RAM. So kind of the same thing that was done for processes needs to be done to your VMs. So if processes on top here is known as the first level address translation, what is this called? Second level address translation, Slat. I would be amazed if some of you hasn't been looking for a new PC that needs to support Slat, because Hyper-V doesn't work without Slat. That's Slat, okay? So second level address translation. Now this can be taken care by your operating system. Every VM needs 1 meg for this page table, or your CPU supports Slat, and your CPU takes care of this. You spare 1 meg per VM. That's why you get more VMs on a machine with Slat than without. So here comes Slat. Now, what happens here is we use 2 slats. So, when your normal kernel looks at a memory address here, we can say that you can read from it, but you can't do anything else. When our secure kernel asks for the same page, it is actually translated to the exact same place. We don't have double memory. We do not have separate memory for these things. They use the same memory, but this is the magic thing of the whole thing here. We can have a different access mask. So on the hypervisor level, looking at the same RAM, we can say that you, sir, you can read this, because you're the secure one. You can read our hashes. So you can authenticate. We can make sure you will know if people should be let into the PC or not. You, on the other hand, are running the normal kernel. We can say the same memory address, sorry, no bonus. You can't read it. So same RAM, same physical RAM, 2 different kernels, totally different end result, which translates into a demo. Let's do this, but we'll do it for LSA ISO. That is, if you're using credential guard, that means that you are trying to protect from pass-the-hash. You actually get an invalid access to memory location. That is a physical error. That's below the kernel. That's below the whole operating system. It's kind of like having a physical switch saying that you do not have access to that memory. It doesn't exist for you. Now, if you can't fork the hypervisor, so if someone steals your hypervisor, they will steal your hashes. But if you keep your hypervisor secure, no one can get to your hashes. If you go to Paula's session, Paula will tell you about device guard probably, and you will hear her say, and everyone else who's doing a security session except me, they will always tell you that device guard is kind of, but that's the different thing. If you want to intimidate, if you want to show how scary this thing can be, then you can say that, well, the thing here is that device guard and credential guard can block pass-the-hash, but it only works for domain accounts. Doesn't work for local accounts. That's true. LSA ISO houses the hashes of your domain accounts. I just did an interview before this session in the cubicle there, and they asked me kind of the same question. I told the same thing I'm going to tell you now, which is I will go back to this tomorrow when I have my session on past the hashes, called moving from reactive to proactive security. But the short version here, you do not have a problem with local past the hash if you read the manual back in 1993. If you are like 99% of people and you skip the part where you were supposed to read the deployment guide of NT 3.1, then you might have these issues. Because local past the hash is not an issue as long as you do not have the same password for your admin accounts on different computers. It says it back in 1993, the deployment guide of NT, you never are allowed to have the same password for an admin on 2 different computers. So local past the hash is not an issue if you've done it like the book says. So that's why Microsoft doesn't even try to fix local past the hash, because it's fixed by you just following the guidelines. Domain past the hash is impossible to fix, because that would mean that I would create a different domain user for every computer. Kind of takes away the idea of having an Active Directory as a centralized database. So you don't want to have a domain admin for every computer. So that is a real issue that we have to fix with this. And this fixes it. It hasn't been, at least for now, it is secure. If someone forks your hypervisor, then you're gone. That's why if you hear this, Microsoft says that kernel is also known as ring 0. User mode is known as ring 3. What happened to ring 1 and 2? Back in 1993, many CPUs that NT needed to support couldn't support 4 levels of execution like Intel and AMD do, so they had to skip 2. So that's why they're using the bottom one and the top one. So 3, 0, -1 was invented later. So Hyper-V, meaning a hypervisor, is known as ring -1. Now, if you know this, I will offer you free food at the expo. What's -2? It was introduced back in Intel's 386, so it's been a while. What's level -2? What's ring -2? It's called SMM, System Management Mode. So translates to either BIOS or UEFI. So that's the layer below hypervisor. If you protect your hypervisor, but your attacker can attack your UEFI, they own the hypervisor, which means they own the kernel, which means they own your isolated user mode as well. So the lower you go, that's why MacBooks having that UEFI fault that they had a few months ago, latest one, that's really bad, because then they even own the hypervisor, which owns the kernel. So I'm telling you, this is secure as long as your hypervisor or UEFI doesn't get forked. That's why you need secure boot. That's why you need to have a password in your UEFI. So other security is a onion, different layers. So now what happens in Windows? Okay, well. So what is VSM? It's not a VM, but a functionality possible because of virtualization technology. If it makes you feel better, you can call it kind of semi-almost VM. But it's only if you feel better. So it's really nothing to do with a VM, except that it uses hypervisor technologies to protect the memory. Okay? How do you enable it? You have to choose 2 features. So hypervisor, not the Hyper-V services required for running VMs, but the hypervisor itself, and isolated user mode. Then you have to set a group policy enabling credential card, for example, and then you can see your LSA ISO. So LSA ISO here is a proof that you're running this isolated. Why didn't they just move LSAS exe to the secure side? That's because LSAS is a very old, huge application that no one honestly has any idea of how well it can handle security threats. It was easier to build a new one which has as little code as possible and try to make that new one secure. That's why LSA ISO is a different process. They could have moved it on the other side, but that's harder to go through a big process than a smaller process. So they just wanted to backtrack it very well. And you also have to set it to start automatically. So pcd edit command needs to be run as an admin to set it to start. Then you have 3 things you can put on top of it. We have a few minutes left. So what you can put on top of it are currently 3 things. The most important thing about the secure kernel, you cannot extend it. There is not a single person in this room. There was quite many who could install a device driver and extend the normal kernel, but you cannot extend the secure kernel. There are no APIs, there are no documentation, there's nothing. Only Microsoft can change the code in the secure kernel. You cannot extend it with a bad driver. That's the main thing here. That's very important. So we can put 3 things there currently. It is a place where Microsoft can put things that have secrets that need to stay secret from you. And there are 3 things. 1, credential card, LSA ISO. So that stores the hashes of your domain accounts. Then there's half of device card. Device card, think about AppLocker. If you know how AppLocker works, AppLocker has a rule set of what can be run on this computer. If you listen to me at all, you can quite easily understand that if that AppLocker rule set is in your memory, anyone accessing with admin rights can just change the rule set. It resides in your memory, so any driver can just change those rules. That's why AppLocker isn't that safe if you're running as an admin. Now, device card has the same rule set, so it has a white list of what can be run on this computer. And then what we do is we take that rule set, but we store it in the secure kernel. Even your admins cannot access it. Which means device card, super secure, super hard to manage, only 1 policy per computer. If you hear any Microsoft marketing people telling you that device card will make your Windows 10 so much more secure that you should investigate and deploy it to all of your computers, do not listen to them. You deploy it to things like ATMs, kiosk machines. Very good example, Microsoft themselves. I asked them at Redmond, where do you use device card? They have a huge, massive IT department. Where do you use device card? Only on admin workstations that can manage Azure data centers. That's a very good thing to think about. That's how hard and hardcore device card is. It's meant for these very special, never-changing workload computers, not for your fleet of office computers. No. And then there's the third one, which is a virtual TPM, Server 2016. So Server 2016 has virtual TPMs for Hyper-V. So those TPMs, problem here for Microsoft was that they couldn't allow virtual TPMs because TPM specification says that TPM needs to stay secret from the OS itself. So they couldn't put it in the memory because your operating system could access that TPM. So TCG, the consortium doing TPM specifications, wouldn't allow Microsoft to do it because that TPM is accessible by any device driver. Now they can. They put the TPMs inside of isolated user mode, so even the OS itself doesn't know what's inside of that TPM. That's why virtual TPMs work for Server 2016. And now I don't dare to stand between you and the beer anymore. So let's try to wrap things up. There's contact information, my websites, stuff like that, and it's beer o'clock, so thank you.